Good afternoon and welcome back to the second video of this series. In this video, we will be discovering these three tanks with very similar flow rates, and we'll be deriving expressions demonstrating how the heights will respond to increases in the initial flow rate Q1 or decreases, but today we will be increasing it by 20%. So let's go ahead and get started. Like I said, we have three tanks, and we have an initial flow rate Q1 of 0.1 meters cubed per second. That is going in the tank 1, and it has height of H1. And then it flows through the small hole that we're calling AH, which is 0.01 meters squared, so very small. And we have the flow rate Q12 going into the second tank. And then subsequently, that one has H2 height, the same area of 1 meter squared for the whole tank, and then again goes through the small hole at the end and flows into the third tank, and then the same thing for the third tank, and then it has a third flow rate that goes, or a fourth one, because Q1, Q12, Q23, and then Q3, which is the exit tank. So with that being said, let's go ahead and get started. So we're going to go ahead and do what we did in the previous video. Start with dV over dt, obviously, because we know what that is. You know that dV dt is simply the difference in the flow rates, right? So easy, for the first tank would be Q1 minus Q12, right? Then subsequently, for the second tank, we would have Q12 minus Q23, right? And then for the last one, for the third tank, we would have Q23 minus Q3. Obviously, these aren't equal to each other, but these are the three expressions that we will be using later on for our Python code. And then we can go ahead and continue with what we did in the previous video with finding dH dt, the change in the height respect to time. So dH dt, and we can do this because again we know that dH or dV dt is the same at, or is equal to dH. Let me just write this down. I'm sorry. dV dt is simply equal to dH dt multiplied by the cross-sectional area. There we go. Sorry, AC. If you multiply these two together, we get B, right? So we can go ahead and use that for our advantage. So we know that H1 is simply going to be equal to this divided by AC, right? Because AC would be on this side, and just bring it over. So H1 would be Q1 minus Q12 divided by AC, right? Then subsequently we'd have the change in H2 respect to time would be Q12 minus Q23 all over AC, right? And of course we can do the last one for DH3. DH3 over DT, we get Q23 minus Q3 all over AC. Those are three expressions for change in heights with respect to time. And then now we can, the only thing we're missing is values or expressions for our flow rates, right? We don't have anything to plug that in for in our expressions on Python. So what can we do for those? Well, we know that Q1 already. We know that's 0.1 meters cubed per second. So that's nice. We only have to figure out these other three flow rates, right? And then, of course, we're going to know how much we're going to change the initial flow rate, and that will obviously change the flow rates subsequently. So we have Q1, or Q12, Q23, and then Q3. Right. these are our three flow rates. And if we know what flow rates are, is the volumetric flow rate, so we need, is literally in the words, the volume or the area that it's crossing through, which is this AH, 0.01 meters squared, multiplied by the velocity. And if you remember from the last video, we derived that the velocity is equal to the square root of 2gh, right? Because again, in here, the viscosity that we're using is negligible. We're using the same liquid throughout, so that does not affect us. So, with that in mind, we can go ahead and plug that in for a value. So Q12, again, our AH are the same for all three boxes or containers. I forget the name, I'm blanking, sorry. So that's going to be the same for all three. AH, multiplied by the respective square root of 2gh, whatever their height is. So for the first one, it would be 2gh1. The second one is 2gh2, right? And then for the last one, it's the last height, 2gh3. So there we have it. These are our three expressions we'll be using for flow rates, and then these are three expressions that we'll be using for our changes in heights. So I'll see you shortly in the Python. Hello, and welcome back to Collaboratory. Now that we've finished all those expressions, let's go ahead and get a code out and see what this looks like in real time, right? So what I have is our previous document and our previous part. I'm just going to copy and paste some of these. No need to type these out. We all know what these are. We're going to be using solid IP, as we all know. And then also just going to use all these constants, might as well. Except our top, our bottom don't exist anymore, as well as H total, right? These are all the same. And then we have AC, right? And then I have my board still up back there. ACS is 1 meter cubed. And then H, T, end, F. Yeah, that's everything, right? Oh, Q, N, yeah. Yeah, we look good. Alright, and then we have this value for HO, right? Let's see if HO is all good. Double check since that was our issue last time. Then now we can go ahead and replace our value for Q1, right? Or new Qn value, right? Because we're multiplying that times F like last time. Shift enter on that, so now we have our new flow rate. Then again, we want to do our right hand, or we want to solve IVP, right? So we want to do three different equations for up there, right? So we're going to do define right hand side rule, or right hand side, we call it, RHS, and then we're going to pass to it, the only variable is time, and then we're going to pull the vector, right? And the vector, of course, are going to be the three different heights, H1, H2, and H3, right? That's going to be equal to the vector. And then, like in our previous video, instead of putting these things in, we're going to be putting in our equations with H1, H2, and H3 with these Q1, 2, 2, 3, and 3 are flow rates, right? So, say Q1, 2, right, is equal to, we're going to have AH multiplied by 2GH1, so we have do, instead of square, I'm going to do it multiplied by half. So 2 multiplied by g multiplied by h1, and this whole thing by half. Right, not this whole thing, but this second part. Alright? Yes, and then we can go ahead and copy and paste that line throughout, because we will be using similar for values for 2, 3, and Q3, right? The only difference is we're adding H2 and H3, right? So there we have it. All we need left here is to return value, right? And what we want to return here is an array, right, of our H1, H2, and H3 values, right? Or no, we want the difference between these, right? We want to do the Q1 minus Q2 divided by AC, right? So we want to return do Q1 minus Q12, that whole thing divided by AC, right? And then again, Q12 minus Q23 divided by AC. Oh, AC or H? The volume. Yeah, no, AC. Yeah, that's correct. For a second, I thought I missed. But okay, so Q23 minus Q3 divided by AC. That looks good. That's what we want to return, right? Alright, I think that looks good. Okay, so we can move on from there. Again, here what we did, then go straight to solving for IVP, right? And then go straight to plotting. So I'm actually gonna again copy paste this just for time's sake. But again, we're gonna call a result, and we're gonna be calling this IVP instead of DHDT. Of course, we'll be using the right hand side equation. This one we just put in. Of course, we're going still 0 to Tn, which is 5,000. Then the array, instead of just H naught, we're gonna have 3 of these, right? Because we have 3 different or 3 heights or 3 different tanks. We're gonna keep the dense output, but we're also gonna be adding a order. What is it called? Let me see. Method, right? New method. It's called LSODA, and these basically goes back and forth between 2 different equations, 2 different people who came up with them to see what works out best. You can go look it up. It's very useful. So I'm going to go use it in here. So that should be all good. And then again, we can go ahead and start plotting this stuff out, right? Okay, so again, I'm going to call it tplot, MP line space. We're going to go 0 to 2 Tn, say 100. And then here I think we should have H1, H2, and H3, right? Result solution tplot. We want to take out this 0 actually, right? I think this is. Let's try it. I'm actually gonna copy and paste these. Alright, just to make sure. Let's see. Yeah, that should be good. Okay. Should make subplots. Fig1.add scatter x tplot, and then we're gonna have 3 of these, of course, right? For each of the individual heights, or for each of the individual tanks, right? This is gonna be H2, H3. And then there we go. Then we can rename this to tank heights, and then again it's time on the X, and then height on the y-axis, so this should be all good. I'm gonna go ahead and give this all one last runtime and see what this spits out. There we have it. Or actually, let me change this. Actually, name equals tank 1. Name equals tank 2. Just for beauty and clarification purposes. Can't hurt. There we go. Our 3 tanks, starting off from 0 seconds. You can see, if you really zoom in here, they all start off roughly at 5 meters. And then of course the blue, this blue line, which is our first tank, tank 1, of course is always higher than the others at the respective time. And that is because it is the first tank, so obviously that one is filled up first as well, and then when it's filled up, it equally constantly pulls out the liquid until the other ones are also constant. And as you can see, it comes off roughly around 1,000 seconds. Zoom in here. You can see over 800 starts stabilizing, and then at 1,000 it's pretty much all constant from there on out. That's pretty much hardly changing. So yeah, there you have it. And then thank you for watching. I appreciate the views, and then come watch the next video where we will be using a proportional controller in the third tank to measure the change in height. So make sure to come check that out. Thank you.